Have you ever actually wondered what's on the final exam for someone who designs computer chips? Well, today we've got one. And we're going to treat this thing less like a test and more like a mysterious artifact, kind of like a treasure map that reveals the fundamental secrets of our digital world.
Because that's really what these questions are. They're not just some dry academic exercises, they are the foundational puzzles. I mean, the solutions to these very problems are running your phone, your laptop, and the entire internet right now. So yeah, let's dive in and see what's inside.
All right, so our guide for today comes from Northeastern Hill University's Digital System Design course. And this test, it gives us the perfect roadmap. We're going to tackle 4 key areas. We'll start with pure, raw logic, then we'll see how that logic is used to build circuits, then learn how those circuits talk to each other, and finally, how they talk to us.
First up, the language. Before you can build anything digital, you absolutely have to learn the language it speaks. And it all begins with a very special, and actually a very simple kind of math.
So here's question 1, pulled right from the paper. Now I know, that looks like a complete jumble of letters and symbols. But stick with me here. What this is really asking is for the student to translate this complicated-looking statement into the simplest possible terms a computer can actually understand.
So this language they're using, it's called Boolean algebra. And you can just forget about complex numbers for a second. In this world, there are only 2 values, true, which we just call 1, and false, which we call 0. That's it. Every single decision your computer makes, from the biggest to the smallest, boils down to this incredibly simple 2-word vocabulary.
So why does this matter? Well, this isn't just some abstract math. This is the absolute alphabet of all digital technology. Every logic gate on every single microchip is basically a tiny little machine that does nothing but solve a Boolean algebra problem. Mastering this stuff is like learning your scales before you can play a symphony. It's step 1.
Okay, so now that we have this language of ones and zeros, what can we actually build with it? Well, the next question on our map shows us exactly how this pure logic starts to become a tool that can actually calculate things.
And here it is, the next challenge. The key words here are full adder circuit. See, the student isn't just solving an equation on paper anymore. Now, they're being asked to design a real component that can perform the most basic of all mathematical operations, addition.
So what in the world is a full adder? Well, it's a tiny digital machine. Its only job in life is to add 3 simple bits together, 3 ones or zeros, and spit out the answer. Now, imagine billions of these little guys all working together. That is what allows the processor in your computer to do mind-bogglingly complex calculations.
You can think of it like this. A single adder is pretty simple, kind of like one little gear in a giant machine. It can't do a whole lot on its own. But when you combine millions or even billions of these tiny, perfect little gears, you get the immense computational power that runs our entire modern world. Okay, so we've got a language and we've got some basic building blocks. But what happens when different digital systems use slightly different dialects? Well, you need a translator. And that brings us to question 3. The task here is to design a converter, specifically one that translates a standard 4-bit binary code into something called gray code. It's a classic digital translation problem. So why have different codes in the first place? Well, gray code has this really cool special property. When you count up, only one single bit changes at a time. This is incredibly useful for things like mechanical sensors, where a tiny little misalignment could cause a normal binary system to totally misread a number. Gray code basically prevents those kinds of errors. It's a much safer way to count.
And you know, this perfectly shows you how engineers think. To solve this, a student follows this really clear process. First, you define the translation. Then, you map out every single possibility in a big table. From that table, you come up with the Boolean equations we saw earlier, and finally, you draw the actual circuit diagram. It's just this beautiful logical flow from the problem straight to the solution.
All right, we've covered a lot: logic, building blocks, and even translators. For our final section, let's connect all of this to something we see and use every single day: a digital display. This is the last puzzle on the test paper. And honestly, it's my favorite, because this is the one that bridges the invisible world of ones and zeros with the physical world that we can actually see. The goal is to design a decoder for a 7-segment display.
You know those displays, right? The ones made of 7 little bars that can light up to form any number from 0 to 9? Well, this circuit is the brain behind them. It takes a number in binary code from the computer, and it figures out exactly which of those 7 little segments to light up to show you a number that you can actually read.
And that right there is the big aha moment. Every single time you look at your digital alarm clock or your oven timer or the display on a gas pump, you are looking at the physical result of this exact type of circuit in action.
It's really just a simple but elegant translation. The computer's over here thinking in a code like 1001, and this decoder circuit instantly knows which specific segments to light up to show us a perfect number 9.
And that's really the secret of this whole exam paper. It shows us that this incredibly complex digital world that we all live in, it's really just built from a few simple logical ideas, layered one on top of the other, a language of ones and zeros, some simple adders, translators, and decoders.
So, the next time you glance at a digital clock or you use a calculator, just think about that elegant logic firing away just beneath the surface. The answers to these very exam questions are all around you, silently powering your world. So I'll leave you with this. What part of your world are they running right now?